Students, now we are going to start the next method, and that is the Gauss-Seidel method. And this is also very simple method and just uh, very close to the Jacobi method. But there is a small difference here. First of all, let me tell you that this is rather fast converging method as compared to Jacobi method. And what is the new thing here? The idea is very similar. First of all, we have a system of linear equations, and you write and again the idea of the two assumption is same, and then even the idea of getting the value of the diagonal variables is also same, like you calculate x1 from the first equation, x2 from the second equation, x3 from the third equation, and similarly you can find out all the values, but start with the initial approximation just like the Jacobi method. Till this point, this is exactly same as the Jacobi method. Students, then what is the new thing here? The new thing is here that what you do is, students, you calculate the first value x1 just like the Jacobi method. The first initial approximation is there, for example, 0, 0, 0, 0. So this was the initial approximation. Now for the first approximation, you calculate the x1 value just like the Jacobi method. But now you have computed a new value of x1. So to calculate the x2 value, you use the previous latest value. Whatever the latest value is you have calculated, just put that one in the system. So you will have a new value for the x2. Similarly, now you have new x1 and new x2. So use these two values to find out new x3. So in the similar way, you use the latest value. Student, this is very important word, that you use the newest value, the latest value of whatever you have calculated, and use that one in the new approximation, in the new value, in the new variable. So in this way you get the solution. So that's why, since you are not waiting uh, to use the previous all the previous approximation, so you are use the new value. So that's why it is rather fast converging. I guess it would be much better if you see the example, and then you will better understand, inshallah. But let me further explain you, students. So this was the here you can see that this is the system of equations I have rewritten here. So this is the same system as I have written in the Jacobi matrix, but no problem, you can write your own new system. And now, students, what it says, again the same thing, if the diagonal elements are non-zero, each equation is rewritten for the corresponding unknown. That is, the first equation is rewritten with x1 on the left hand side, the second equation is rewritten with x2 on the left hand side, and so on as follows. So student, the idea is same. So c1 is this one, a12 x2, a13 x3. Similarly, student, x2 is equal to this one, xn minus 1 is this one. So all the things are same here. So students, what is the new thing here? Let me tell you. So this is important. See, now you use x1 as usual. X1 as usual. You just start, for example, with the initial approximation, that is 0, 0, 0. So you start with 0, 0, 0 here. No problem. Now, when you have x2 here, student, I guess I need to highlight this one. So x1 is 0, 0 same, but this one for the to calculate the value of x2. So now this is very important, that for example here x3, so you must, this was the old one. Sorry, let me I guess it's better if I erase this one. uh, and let me choose the different value here. Just wait, please. Student, I think, yes. So this was the new value. X1 was the new value here. This was the new value. So you use now not the initial approximation, you use this value, X1 here. You use this X1 here at this point. Similarly, for the new value, you use whatever you have calculated here, use these values. So in this way, you get all the values for the new approximation. So students, let's see an example, and hopefully this will definitely help you to find out the solution of the linear system of equation and using the Gauss-Seidel method. So students, so this is the same system basically. This is not the new system as you have used in the example number 1 for the Jacobi method. So let's solve this one. So students, for your convenience, I have rewritten the system again as I had written it in the Jacobi method. So what I am going to do is, so the first initial approximation students is 0, 0, 0 as the initial approximation. Now we obtain the new value of x1 students. So what is the new value? Again, we have here we had x2 and we had x3. So we use the same initial values. So that is minus point. So now students, we have a new value of x1. See, we have a new value of x1. So it's written here. You have a new value of x1. However, use it to compute a new value for x2. That is, student, now x2 is equal to 2 by 9. See in this formula, 2 by 9 plus 3 by 9 into x1. Now x1 should be not zero value. In the Jacobi iteration, you were using the previous value 0, 0, 0. But now in this case, you are using the new value, whatever the new value is. So you will use the new value here. So x1 here. So student, what was the x1 value, new value? Minus point. And x2, sorry, x3 was, you didn't calculate yet. So use the previous value and that was the zero value. So that is 0.156. So similarly, students, now the new values are x1 is equal to minus zero point 0.2 and x2 is the new value here, that is 0.156 to compute the value of x3. So x3 is equal to this, you put this value and this value. So that is minus 0.508. So students, in this way, so the new approximation is this one. So in this way, you quickly converge to the solution. You get rather fast, rather quickly towards the solution as compared to the Jacobi's method. So student, here this is the table for the approximated values. So for n is equal to 0. So you have the initial approximation. For the first one, you have these values minus 0.2, 0.156, minus 0.508, and then 0.167, 0.334, minus 0.5429. Similarly, you get the fifth value to be same as the fourth approximation. So you get the same answer. And students, see, using the Gauss-Seidel method, you have only the 5 approximation to achieve your answer, to achieve the same accuracy. Whereas for the Jacobi method, you had to made 7 iterations. So you can simply say that this is rather faster than the Jacobi method. So student, this was all about the Gauss-Seidel method, but for both the Jacobi method and the Gauss-Seidel method, sometimes it happens that your solution does not converge. Your solution start diverging, means you are going away from the solution. So you don't get the solution. So in order to make the solution convergent, so there is a condition. But before the condition, let's see an example where the solution is simply diverging. So students, see here. So this is the example of divergence. So just consider this example: x1 minus 5x2 is equal to minus 4, 7x1 minus x2 is equal to 6, and use the initial approximation to be 0, 0, and show that the method diverges. So students, just like the previous step, as you have already done in the previous example, so calculate the value of x1. So x1 is equal to this one and x2 is equal to this one. Now if you use the initial approximation, you get x1 is equal to this one, so answer is minus 4, x2 is equal to minus 6. As the first approximation, repeated iterations produce the sequence of approximation shown in the table 10.3. Student, this is important that you are using the Jacobi method, but if you use the Gauss-Seidel method, even then you will get the divergence. So let's see the table now where the results are there. So students, here you can see the first approximation give you this, the second approximation give you this, the third this, fourth this, fifth this, sixth this one, and seven. You see it's going very far away, very far away, so you are not converging basically. So it means, so this solution system was not converging in this way using this method, but it was diverging. So student, in order to make the system and to see whether the solution will converge or not, so there is a technique to check, and that is the technique, and that is called strictly diagonally dominant matrix. Students, I will tell you what is the definition of this one. But if your matrix in the beginning, you can see whether the system will converge or not, so you don't need to solve the steps. You just check with the first step, with the check that whether this is strictly diagonally dominant matrix or not. If it is diagonally dominant, strictly diagonally dominant matrix, then the system will definitely converge. There is a guarantee that the system will converge. And if this is not strictly diagonally dominant, then there is a chance that it will diverge. And so let's see, students, what is diagonally dominant matrix. So students, this is the diagonally dominant matrix. So what is the definition here? It says that an n cross n means a square matrix is strictly diagonally dominant if the absolute value of each entry on the main diagonal is greater than the sum of the absolute value of the other entries in the same row. Students, what do you mean by that? It says that, so these are the diagonal entries, like the diagonal entries. So the diagonal first entry is for the first row is a11, so that is a diagonal entry. And if you take the absolute value, means you don't need to consider the negative values, you just take the absolute value, and this absolute value should be, if it is greater than the sum of all the other values in that row, all the other values in that row. And similarly for the second row, a22, for the A22 students, if it is like greater than all the other values. Similarly, for the last one, it is if the last diagonal entry post absolute value of the entry is greater than the all the other values. So you can say that the system, students, is uh, you can say that it is strictly diagonally dominant. So students, this was all about the uh, Jacobi iteration method and the Gauss-Seidel method. And this was the important concept in this last slide, that if the system is diagonally strictly diagonal dominant, that it gives you guarantee that the system will converge to the solution. So students, these are the exercise questions for you. So you need to solve this one. And I guess there is one more question in the next slide. So this is the question as well. So students, just do these questions, and these are the practice questions for you.